there's some really, yeah, we can talk about it some other time. There's some really weird, interesting things on this that I'm encountering as I go along here.
Mm.
Yeah, you've probably realized it that when like there's just these weird blind spots that just
Yeah, it happened a lot.
yeah, that was the big one, right? But we worked through most of that, so it worked out pretty good. Okay, so one of the things I want to point out here is basically all solutions will have, or I should say, all real world systems are going to have these two forces, the reflections and the scattering. Okay, but in terms of scattering you and reflections, you typically need different phases for that to happen. So, for example, if you have a solution that mixed very well and it has just an aqueous solution, okay, then what's going to happen is you're going to have very little scattering, okay? And you've seen this before. So, probably in the ones you took, actually, probably were pretty decent. So, where you basically don't see any light coming out of that solution at all, despite the fact there's a beam coming through, right? Because you're not looking directly at where the beam's going. Okay. If you were to go the other side, look here, right? You would actually see reflections coming off. Okay, like you're shining a light at flashlight at a window, right? You see reflections coming off at you. You go to the side, you don't really see much, do you? And so scattering is the ones to the side. Okay, reflections will be directly on. The reflections will happen due to the phase changes at the boundaries. Okay, so the cuvette in this case, right? But if you had any other system of boundaries, you would also see reflections off of those. Okay. Now it happens because of the difference in the refractive index. Is that making sense? Okay. So if you have the exact same refractive index, it won't happen. And if you have it very close, you'll minimize those. Right. Scattering, on the other hand, this is because you have particles suspended in there. We have phase boundaries essentially scattered throughout the solution. And so these are going to be fairly small particles. If it's a big phase boundary, you'd get a reflection off it. If it's a small one, the light can kind of wrap around a bit. What we're going to get is because it's going to hit these odd parts, it's going to go like this. And you're going to get scattering, which is just randomized throughout. You will get scattering patterns sometimes. But what you will see here is this is what's called usually a bloom. Have you ever seen where they take like soap water and they shine a flashlight through it? Have you ever seen it where you can see the beam going through the solution, like the pathway, or where they like shine a laser through smoke, and so like you can see the beam? Okay, that's scattering. You're seeing the beam because it's scattering to your eyes. Does that make sense?
Yeah.
Okay. Okay. This right here is nanoparticles mixed in. That's what's causing this scattering right here. Okay. See what it does to the entire spectra right here? Can you see that okay? And so, like, what we see here is that the light that scatters more ends up being scattered off, and you get these very large absorbances, even though you don't have anything that's really absorbing that region. Okay. Stuff less scattering, usually bigger wavelength stuff, scatters less because the wavelengths will be able to avoid those small particles. In this case, the nanoparticles are probably about this size-ish, somewhere in this range. They're avoiding that, and so they get scattered less, meaning more of it makes the end. Does that make sense? It is something you really need to understand, though. So the irradiance of the light that passes through a reference cuvette, we're going to measure that with pure solvent. That's typically denoted as P0. Okay. And basically what we're doing here is we're taking this power incoming, and what we're doing is we're correcting that with the background by using this cuvette with the same solvent we're going to use. Ideally, you would have almost everything you want to look at except for your sample. Okay? The specific thing you want to take the spectra for. In this case, potassium permanganate. That would be called a matrix background. Okay? because it has everything else in the matrix. Right? But you can also just use the solvent if the matrix is not convenient, and that will remove most of these boundaries and most of these interferences. Okay? And so you may have used water with that in Snelling's class for the general chemistry. Yeah. Okay, so you're going to use these P0 and P. The irradiance that passes through the sample is going to be P. That's the actual sample one. And those are going to be used to do the T and A. Now, your reference cuvette, this will actually give you most of these reflection absorptions. This will give you those for the cuvette and the solvent. If you introduce anything else, those will not account for those. Okay? So, for example, if you have solid suspended in here when you put in your sample, you will have scattering that'll happen from that solid that's suspended. Okay? Okay. So when we record an absorption spectrum, this is typically going to be a two-part process. You're going to record a baseline spectrum. That's going to be used with reference solutions for both the sample and reference cuvettes. And then you're going to subtract your baseline absorbance from the sample absorbance. This is going to obtain the true absorbance at each wavelength, and will give you some negative artifacts, but for the most part, you're going to get the baseline subtracted off, which will get rid of the vast majority of those scatterings. It'll also get rid of the absorbances in the solvent, if you have any absorbances in the solvent, though do try to minimize those because you are subtracting off, right? Keep in mind that if you would normally, let's say we had a very dark solution, we're passing a light through it. If you would normally be like a 1 absorbance, when you subtract it off, that difference with your spectrum is going to mean you're going to have very tiny peaks. Okay? It's going to be very difficult to see any real responses. Does that make sense? Yeah. Okay, so some of the practical tips to keep in mind, these are usually in an SOP that would be in your lab. If you have to generate this, you want to know. So allow the spectrometer to warm up before use, just like a light bulb turning on. It doesn't reach its brightest point right away. Okay. It also is very unstable when it's first turning. In terms of like electricity, flickering, that sort of stuff. It's going to be its worst time. Analyze a calibration check standard to determine if the calibration is still valid. So you take a full round spectrum where you do the baseline and then you correct the baseline, subtract it from a sample. And that sample would be something that you know the peaks for. And so you should know that you should get this spectrum from that. And then you look at that. Do my numbers line up? Yes. Okay. If the numbers don't line up within a range, you have a problem. And you have to do something to remediate that. You need to keep containers covered to exclude dust. Dust obviously can play quite a major part in this because, again, if you have dust in your samples, if you have dust in your system, this is going to cause scattering, isn't it? Yeah. Handle cuvettes on the frosted side. What do you leave behind every time you touch something? Yeah, exactly. Oils, right? And so oils oftentimes are going to interact with spectrum. Okay. So very, very common mistake that's made. Rubber gloves even are not necessarily a complete cure for this, because they can also pick up things as you use them, right? So use the sides you're not going to be using for the spectrum. If you see anything on those sides you're going to pass the light through on the spectrum, you need to clean it, okay? And it needs to stay consistent for the reference and the sample. Use a tissue to avoid putting fingerprints on the faces. If you need to handle the faces for whatever reason, you would take, the tissues we have in lab? The chem wipes usually, though there are better tissues you can get than chem wipes. You would use those to hold and manipulate it, okay? Do you know why you use tissues? Partially not to leave residue, but also partially because you don't want to scratch it. So like if you were to use like tongs or something, you would scratch it up, right? So some of these can be quite fragile. Place cuvettes in the spectrometers as reproducibly as possible. So be very careful that you don't like end up placing these things in where it's like this one time and then down further the next, because the thickness is not going to be uniform or exactly uniform throughout, right? It's going to be their best they can do, but within a range. So this is the Beer's Law chemical analysis. You did a really good job on that. So there's kind of four major ways we're going to have an analysis that can be done for the spectrometry. There is directly on an analyte. If it absorbs at a unique wavelength, you want to keep a consistent wavelength for all of your analyses, because this is going to give you, the extinction coefficient changes, right? Depending on the wavelength, right? After converting the analyte to a product that absorbs a unique wavelength, this is typically done for something that you can't detect with the instrumentation you have. And so, for example, we actually were looking at that one where we were like binding proteins and enzymes. Remember that? Where we had the antigen binding? Yeah. So you can actually like bind it with a fluorescent marker, and then you can do the spectrum of the fluorescent marker. And so that will give you a very consistent wavelength you can follow. And then in whatever amount you have bound, well, that's the amount you have of that substance, right? But there's a number of different ways. For example, you can actually do some really cool studies where like you monitor iron levels by using things that can bind iron and turn color, right? You can use indicators to do this because they turn color depending on the amount of your substance, right? So on a mixture of analytes that possesses different absorption spectra by measuring the absorbance at multiple wavelengths. So this is a typical like full spectrum you would see from organic chemistry. Okay. By separating the similarly absorbing analytes using a technique such as chromatography, so the absorbance of each analyte may be measured individually. Do you remember chromatography at all?
Yeah.
Okay, so you get separation depending on how well it moves, right? You can do this with mass MS, of course, but that's GCMS, right? And probably the one you would recognize the most from organic chemistry and all those. But you can also do that same thing. You can use a chromatography column like biochemistry, and you can use UV vis at the end. You can use infrared, and you just look for one peak that you already have a curve established, and then you can see, how much comes off of those different species as they're coming. Okay. And so it gives you a separation method to look at the individuals coming off. That making sense? Yeah. So you can actually combine all of these different methodologies, the separation purification methodologies, which we'll go into more detail later, and the electrochem also combines it. And you combine the spectrophotometry that we're using right now. Okay, this was the problem we did at the beginning of class. That's the answer that you got. So, this would be the problem where we would use the path length here that has a different path length to figure out the concentration. And so what we would do again is we just use Beer's Law again. We'd have to use that molar absorptivity for that wavelength. Always make sure your wavelengths match, by the way, because if your wavelength of your light doesn't match, the molar absorptivity is different. And so we plug that in. That's the previous number we got from the previous problem. It's a path length of 5 centimeters now. And this right here is that absorbance. And so that's going to give you your concentration. And then you can always convert concentration units. So in this case, we want to go into milligrams. That would be your C6H6 molar mass, of course. Okay, and that's that. Does that make sense?
Yeah.
Okay. This is a serum iron determination. And so serum iron has 3 steps. You're going to reduce the Fe3 plus and transfer it to Fe2 plus. This would actually release it from the protein, so then we can see we can actually get the iron. We're going to then add trichloroacetic acid and this is going to cause to the precipitated proteins. What's going to happen then is you're going to leave the Fe2 plus in solution. If you centrifuge the mixture, all your currently suspended proteins is going to go down to the bottom and form a pellet, and then you can just get the supernatant with the iron. Okay. Once we get the supernatant with the iron, what we can do is we can then measure the volume of the supernatant liquid from our step 2. We put that into a fresh vessel. We're going to add buffer plus ferrazine to form a purple complex. Where the hell did my water go? And this is going to have an absorbance at 562 nanometers. This is actually what this looks like if you take the entire spectrum. And see how that's your strongest peak right there? That's going to typically give you your most sensitive response if you're trying to look for the amount of something. Okay? So if you're doing something new that you've never done before and you don't have a procedure for, what you would do is you do a full spectrum, and then you choose your lambda max, your maximum wavelength. And if you have other species that you have to be concerned about, you do have to be careful that that lambda max doesn't correspond to something else that's in your matrix, okay? And then your lambda max is what you would then measure all the other absorbances for your Beer's law determination. Okay, so this is the serum copper, can also form a colorful complex with ferrazine. And so when you're looking at this, this would also be detectable if you were just had that copper plus right here, okay? So that would cause problems, obviously, right? We would get a false indication of that iron in serum. So what you can do is this is going to be what's called a masking agent. And so it's going to bind the copper, and it will very tightly bind that in a very stable complex. And that complex has a very low absorbance at the 562 you're going to be measuring at. And so then we can avoid interfering with our spectra by masking that copper. Okay. And so whenever you're talking about reagents that mask something, they're typically going to bind that very tightly so it won't react with the whatever is going to give you your signal. Okay. That's thiourea that you can use, or you can use neocoprian right here. But it's just the same complexing we were talked about last semester. So you just want something that's several orders of magnitude tighter binding, right? So that it won't come out in your other solution. Okay. These are the entire steps. Do you want me to read through those, or are you okay? Okay. So let's try this example real quick and go ahead and do the math and see if you have run into any issues. I'm going to grab my water real quick. Okay, so the first thing I want to point out is whenever you have a y-intercept here, yeah, Beer's law says you should have 0, right? That should be 0. But this is real world. And so you will always have a tiny intercept, okay? Some small y-intercept. So you always use that small y-intercept because it is meaningful data, okay? Because every single one of your actual experiments will not be perfect, and you will always have some sort of systematic error that does get through, okay? It's just a factor of us being human and not magical fairy creatures. Okay. Now, first thing you always have to do is you have to take your sample one, right? And then you have to subtract off your blank. Okay. So that's always the first thing you have to do unless you have it automatically set up for you. Okay. And then what you're going to do is you're just going to plug that into the formula and rearrange and then solve. Okay. So I've actually have it rearranged right here because it's easier to do when I'm typing and stuff. And so I plug that subtracted off right there on unknown into the formula. You got to do the subtraction first and then divide. Note that you are given ones that are in micrograms. And so you got micrograms. And so, excuse me, that's micrograms to grams. And then we're going to use the molar mass of the iron right here. There's not multiples of it, so we don't have to deal with any of that stuff. And then we're going to go ahead and divide it by our liters of our serum right there. And so that's going to give us the molarity. Did anything go wrong?
I just didn't divide that.
Ah, okay. Yeah, so you would have ended up in moles. Yeah, okay. Yep. And that's it. Any questions?
Oh, so
Speak up. Repeater. Okay. All right. So let's talk a bit about preparing standard solutions. Okay. Now this is one of those things where people like always try to think that spectroscopy is like put the thing in, press a button, but that's because all the hard work was done for them. So, like in organic chemistry, all the hard work's done for you, signing the spectra, telling you what bands you're looking for, prepping the instrument, running standards to make sure the instrument's prepped, all that's done for you. And then you just do the end part, and done. And so everybody thinks that's spectroscopy, but it's not, right? The real work of spectroscopy is things like running the per standard solutions, okay? And so when you're doing a calibration curve, for example, you would use 1 milliliter of your standard here. Okay, you don't necessarily have to use 1 milliliter, but in this case, we're going to use 1 milliliter. And we would have it where we have different concentrations. Okay, and you would typically want a pretty nice sort of linear distribution. If you can't do a linear distribution, what you want is a nice where you're closer to the bottom, more points, further out as you go further out. Which is kind of what we have here. Now, when you have your stock solution, this would be then made. Appendix K, by the way, has the way you would do this with an iron wire, which would be a pure iron sample where you dissolve it down. Very similar to what we did in lab with the copper for the superconductor. Okay, basically using an acid to digest the pure iron, get it all in the same oxidation state. And so we would digest that. We're going to get this made up. And so it's going to then give us standards that are going to be about 0.1 molarity HCl for our calibration curve right here. So what I want here is we have this set of conditions. So we have dissolving 1.086 right grams right there. Okay. Iron wire. It's dissolved in 40 milliliters of 12 molar HCl. We diluted it to 1 liter in H2O. And that solution is going to contain that number of grams per liter, okay? This is going to be in 0.48 molar HCl. How can we get to a 0.1 molar HCl for our calibration curve of that stock solution? Okay. Notice that we can't precipitate this, right? So how can we make that stock solution?
can't believe
Yeah, that's exactly it. So we're going to make dilutions, right? What dilutions do we need to make?
that.
Yeah, so this right here is in micrograms, right? And we want that micrograms per 1 milliliter. No. Okay. This right here is grams per liter, isn't it? See that? And so this is going to be, well, 1.086 micrograms per milliliter, isn't it? Because gram per liter is the same thing as microgram per liter, milliliter, excuse me. Okay, so once we know that, well, then it's pretty easy dilution factors, isn't it? So we just need to do a 2 to 1. This is going to give us a 2.172 microgram per milliliter, isn't it? And that would be your 2 that you need for this. Yeah. Okay. Okay. And so we just need to go through and do that for each of these, don't we? So to get the 3 of stock solution, we take 3 milliliters. You would want to use something like a Class A pipette, right? And then we would deliver 3.258 micrograms to that 1 liter solution, won't we? Okay. And we just go through and do that each one. So it's a 4 milliliters delivered, 6 milliliters delivered, 8 milliliters delivered. When you're doing these, you want to keep them as small amounts delivered as possible. And so most times you're going to have something like a 3-4 milliliter ones that you could use. So you end up using combinations for a lot of these. Okay. Rarely are you going to have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 milliliter pipettes. Okay, so if you do serial dilutions, are you okay with dilutions? Okay, are you finding any of this problematic? Okay. So yeah, starting from a stock solution of 1,000 micrograms of iron per milliliter in HCl, 0.5 milliliter HCl, how could you make a 3 microgram per milliliter standard in 0.1 HCl? You only have a 100 milliliter volumetric flask and a 1, 5, and 10 volumetric pipettes. Well, we're just going to have to do the combination that will give us this out of the 100, right? Is you can't go one round, can't you? Because this divided by 100, which would be your maximum one, that'd be a 1 to 1,000, right? Okay. So the absolute max you could do here, right, would be 1 milliliter out of 100, isn't it? So the maximum dilution you can do in one step is to 10. That's not going to get you to 3, is it? No. And so what you'd actually have to do here is you're going to have to do this in a serial dilution, aren't you? Okay. So how can you do that in a serial dilution here?
Well, once you have that, do it.
So there's not like a strict path here, but you're gonna have to do two main things, okay? Um, you could do like a 1 to 100 to get your largest solution, right? And then you'd be at a 10, would you? Okay. And then how do you get only a 3 out of a 10? Well, the next one, this is 100, right? So how do you get a 0.3 out of that? The 1 3 times would give you a 0.03.
Then just
The 10 3 times. Yeah. That would give you a 30%, right? Now you can do it either way. It doesn't really matter. Mhm. Now, if you wanted to do this in more dilutions so you have more options later on, you could. Like, there's no reason you couldn't do a 10 to 100, then a 10 to 100. Then like, it may increase your error by a little bit, depending on your classwork. But like, if you had wanted breakdown in dilutions because you're working in a large lab, you might do that. Okay, let's talk about Beer's law's failures. Okay, where does it break? Where does it fail? Because that's just as important as where it works, right? You need to know where to avoid it. So this is going to work for monochromatic radiation passing through a dilute solution in which the absorbing species is not participating in a concentration-dependent equilibrium, and in which there is no stray light. Okay, those are all limitations on Beer's law. That's when those are all true, Beer's law holds. When they're not true, Beer's law does not hold. So let's talk about positive deviations. So positive deviation would be where you get more absorbance than the concentration. And that's going to be from things like chemical effects typically, and matrix effects are a big one. Okay? So if you have a matrix effect, which would cause you to have less light reach the end. Right? Negative deviations are going to be where you have a smaller absorbance detected than that concentration should give you. Okay. And this can be due to chemical effects. You could have things like actually eating up or reacting with your substance to change it. You can have polychromic light. So if you have polychromatic light, you can end up having less, more light reach the end than you should get. Okay. You can also have stray light. So if you have the top open for these things, sometimes some of it can get scattered back in. Or you can have a very bright light that sort of irradiates the whole area, right? Or you can just have like a gap in your machine or something. Okay. And so stray light obviously would add light to the end. And so you get a lower absorbance. Notice the concentration part of this, by the way. What does it say there? Dilute. This is something that people, when they're first learning this, have a tendency to not do properly. They try to do these for very concentrated solutions and have a lot of problems. Okay, so let's talk about, because I know you guys love titration so much. we got away from it for like a class or two. Spectrophotometric titrations, these are going to be monitoring your changes in absorbance during a titration to tell where the equivalence point has been reached. So it basically, the spectrometer takes the place of your eyes, and it can do it for things that are not visible to you, right? So you can do this with infrared, you can do this with near infrared, anything you want, really. Okay. And it actually is very, very useful and very nice. You can actually automate the process to some degree, where you'll stop the titration automatically if it detects that frequency of light. So this would be an example of this. So here we have MgIN, which is the red chalcogite right here. This is EDTA. EDTA will then pull the Mg off, and this would give you that blue Calamite. You remember this reaction. Not very distinctive to your eyes, is it? Kind of annoying, right? We would have been a lot better off if we went ahead and did this with a spectrometer, because the spectrometer can just monitor these as wavelengths, right? And can then see where we have a peak on our wavelength. And so we can get a very, very easy relationship. So this is what it would look like. We would monitor a peak. Specifically, we would want to monitor this right here, where we're looking for this wavelength of blue. Okay. And then what we would do here is we would just add volumes of EDTA. You can actually set it up to automatically do this, where it just adds like 0.2, 0.1, something like that every time. And as it starts detecting more and more, it adds less and less. Okay. So you can actually automate this system. Do you understand corrected absorbance? What is corrected absorbance? You're subtracting your baseline. Yeah. So subtract the reference spectrum to get these numbers. Okay. So you have your absorbance. You're watching for this peak, this blue quote unquote peak. Okay. Notice that would not be in the blue wavelength that you're watching. You're watching actually for the other wavelength, right? Okay. You know, the thing it absorbs at is not what you see. It's the opposite. Okay. So you're going to get here and you'll see that the absorbance will start going up, right? And then it will level off. And so that leveling off is where you've gone past your endpoint now, and then you can just trace your lines on these two portions. This right here, wherever this intercepts, that is going to give you your endpoint actually. Okay? Which would be around here. Does that make sense? See, that intercepts around here-ish. Okay. This is actually what one of those cells looks like. So what you would do is you'd have your titration, you'd have a little pump or something, and it would take it through into your spectrometer. This right here would be your, this is your path right here. I'm sorry. Let me clarify. Okay. So you have your, this is the spectrometer portion. This normally, see how it's like a long thing like this? Okay. This normally would be like a little probe you can put in. Okay. Or you can actually like clamp it if you're using glass and you're absorbing something that doesn't absorb it. Glass doesn't absorb, that would work well. What you can do is you can actually clamp it onto the outside of your tube. Okay. But you need to make sure it mixes well and that your mixing is not going to interfere with your spectrometer. Okay. So you can sometimes have to get a little bit more complex with this, where you actually like pass sample around and circulate it into your spectrometer. Okay. But most of these systems can actually just be as simple as like you have a container and you can put light through, or you can put a little probe in that looks a lot like a pH meter. Just it's a fiber optics that are connecting the ends that are passing light. I'm actually going to try to get one of these in the near future. They only cost like $2,000, $3,000. So they're not super expensive. And then you have your little path length. That right there would be the path length it's passing light through. Does that make sense so far? Notice this path length is going to be 2 times because you're bouncing it off on a mirror at the end. All right, so this is what that looks like. And so you're going here, you're getting the midway, and then you're getting the blue. Good with that? Mhm. So this is a different way to find an endpoint. So you can do an endpoint 2 different ways. So one of the ways you can do is you can find the topmost point and then go halfway through. Okay. But the other way you can do it is you can draw this line, you can draw this line, and where these intercept is actually going to give you your endpoint down here. Because remember, when you draw this, this has a slope. Okay. So again, it's not super easy to see on there. So if you do this linear one right here, it's going to come out like this, right? This one is going to come out like this. Can you see that a little better now?
Yeah.
So if you do this, see that? It's the same vertical point.
So from where they intersect in the mid.
If you have a smaller one, I think it works a little even more. Okay. So if you go like that, you end up at the midpoint right there. Okay. And it's just a better graphical way of doing it. It'll give you an approximation at an endpoint that's much, much closer. That's easier to do with a machine. Does that make sense? Because machines graphical learning is actually very difficult, right? Really, really challenging. But you can do where this has so you can take the machine and you can do the calculation where you have a delta, a difference, in these absorbances that's below a certain number, right? Or above a certain, excuse me. And then these ones would be a delta absorbance below a certain number. And so if you do that, you can then plot those points, get the slope, take the two equations, take the difference. And so graphically, this is a much more easy way to do this in a R or Excel or Python, or rather than trying to trace this yourself and try to figure out where the middle point is. Basically, it's the math way of doing it. Okay. The absorbance measured after adding 19.9 milliliters VDTA to 10 milliliters drinking water was this. Calculate the corrected absorbance that should be plotted for this. Okay. So, try this out. And let me know if you get stuck somewhere, okay? Okay. Okay. Ready? Yep. Yeah. So remember your volume changes. So you're also diluting it as you go along, right? So you got to be careful about these with titrations because you're adding volume to them. You actually dilute your solution, meaning you reduce your absorbances no matter what. Okay. And so you do have to add that into your corrections. And that's the correction right there. Is you got 10 plus 19, right? And it started as 10, so now it's 3 times more dilute essentially. And so that's the actual what it'd be comparable to. The 1.7 or 0.17, excuse me. I think I got it about right. Right there. Okay, so what exactly does happen when a molecule absorbs light? Remember, I kind of have to teach this like you don't know the inorganic side of this yet because it's not a prerequisite, but you guys do. So I'll try to give you the analytical perspective. Then you can combine in your head with the inorganic perspective. They're both still true. Okay. It's just different ways of looking at it. So when you have a molecule that absorbs a photon, the molecule is going to be promoted to a higher energy excited state. So it's going to be a more energetic excited state. Your structure of your molecule is going to change when the photon is absorbed by the sink. So for in this case right here, we have our excited states here. And this is more along the lines of like a higher energy photon. Okay. So when we do the excited state for this, the excited state of formaldehyde here is actually going to move that oxygen out of that plane. And so we don't really have the normal double bond structure for that oxygen anymore, right? We're actually going to leave behind some of that pi bonds orbital structure. Okay. And so this is actually the excited state for that formaldehyde right there. This is the ground state for that formaldehyde there. And so again, it has that full double bond with the pi bond above and below, right? And when we do this, which is a deformation of that, it's going to actually move that out of the plane, isn't it? Okay. And so that is actually going to partially modify and partially weaken that oxygen carbon double bond. So that right there was what's usually referred to as a molecular vibration. Okay. We had kind of went through the different sorts of excited states you would see for different wavelengths. Note that most of the stuff we're talking about in this chapter would be on the order of like molecular vibration, or it would be like UV vis, where we're moving electrons to different orbitals and molecules. Okay. So these are right here, molecular orbitals. They're going to describe the distribution of electrons in a molecule, and you're kind of used to that probably. And so if we're talking about UV vis light, it's typically going to boost electrons from one of these orbitals into another one. And that would be the corresponding energy of that photon that's being absorbed. And so this right here, molecular orbital diagram. And your molecular orbital diagram, each of the horizontal lines here is going to be one molecular orbital. Each arrow represents one electron, of course. And then the direction of the arrow is its spin state. And so let's say you absorb a photon. It could take something from this non-bonding right here and boost it up into there. Okay. Okay. Now, this is a fairly simplistic, and we don't need to go too much into the symmetry and all that you remember from the inorganic chemistry in this case. Though that is still true, that is still going to be states that are more likely to happen and allowed transitions. Those are all still true. The other thing we're not really considering here is we're not going to consider right now, at least, rotation and your like vibrational. We're just talking about molecular orbital spectroscopy, okay? So this would be like visible light and some UV.
Really no infrared.
You can have a few different molecules, like the higher energy infrared might do a little bit of this, but for the most part, no. Not really talking about infrared. We're saying this stuff. Yeah. So infrared would be orbitals. They would be not orbitals, excuse me, energy levels that would actually be clustered around these energy states. They'd be smaller transitions. Does that make sense? The smaller energy light. Now they do actually cluster around these, like some of the bending and stretching motions will kind of play between two orbitals. And so they very much feed into each other, but it is a slight difference. Okay, so this is electronic transition. This is where an electron goes from one energy level to another. And so, for example, you see some examples here. This is actually going to change between singlet excited state and triplet excited state here. So A 355 nanometer photon will actually promote the formaldehyde into a singlet excited state. A singlet state is going to be where the electron spins are opposite of each other. And so you have two different spins. And that's going to be a singlet state. So in a magnetic field, a singlet state is actually going to remain a single state because you're going to have the up and the down, and they're going to be energetically equivalent because they're not interfering with each other. Okay. A 397 nanometer photon, on the other hand, so 42 nanometer difference, is going to promote a formaldehyde molecule into a triplet excited state. And so a triplet state is going to be where the electron spins are actually parallel to each other. And so you have the same direction on both of those different electrons. So you have the two electrons in these two energy levels here. And so they have the same direction to them. That's going to give you a triplet state. Now, in a magnetic field, a triplet state will actually split into 3 energetic states. Okay? And so you'll see 3, a triplet. Do you remember NMR at all? Yeah, so this ends up playing a lot in NMR. These spin states, coupling. Okay, so they don't, actually. So what usually has Hund's rule is general chemistry, obviously, but and it was a rule that essentially said they're going to be energetically equivalent. Okay, and which state they're in at that point didn't matter. Yeah, and so you always put them all in just the same state across, no matter which way. Okay. And notice that there is an energy difference in there. So, like, this is an energetically favorable state here. Mm-hmm. Yeah. Takes less energy to get there, right? I'm sorry. Other way. God. Other way. This being where they're not paired, same spin, took more energy to get there. Yeah, sorry about that. God, I need more coffee or something. Okay. This one, where they're paired, actually required a longer wavelength photon, right? A less energetic photon to get to. Yeah. And so this was lower energy. And even the energy levels here, you can see, are lower. So that was the lower energy state, but just because it's the lower energy state, Hund's rule was for generating the lowest energy ground state, right?
Yeah.
Yeah. We're past that. Yeah. But if you want to generate a ground state, Hund's rule will still work very nicely. Okay, so the infrared and microwave radiation, they're not energetic enough to induce electron transitions in most organic compounds. Okay, and so they're still going to induce transitions. The infrared photons are going to induce transitions that we refer to as vibrational states of motion of the molecule. And those are going to be those vibrations like the deformation, the stretch, and then you can combine those things out. Anti-symmetric, symmetric stretches, etc. Microwave photons are going to induce transitions that will be between rotational states of your molecule. So they're going to rotate, and that will be the transitions you're going to see. Okay. This right here is some of the different infrared states that you're going to see. This would be your like bending right here, CO stretching, that sort of stuff. This is for that same molecule we were just talking about, the formaldehyde. Yeah. And so you probably recognize those from organic chemistry and inorganic chemistry as well. We did a little bit of that. Okay. So there are the product of 3 axes in space, of course. So the number of atoms in a molecule. This is going to give you a number of vibrational, rotational, and translational states for that molecule. So if we have n number of atoms, the number of different motions we can make then with those atoms would be 3n. 3 dimensions, and n being the number of objects that can move around, right? If it's linear, then because it's linear, 2 of those are going to be the exact same thing, right? So if you have a linear molecule, it really doesn't matter whether you're doing this or whether you're doing this, right? They're the exact same one, okay? They're degenerate. And so 3 of those states will be translations, because the translations doesn't change from the linear, does it? Me moving this right or left, up or down, or towards you, back from you, still same movements, right? The 2 states are going to be rotational. This would be the x and y axis. Remember, the z axis is specially designated. And whenever you're writing these out, and that's your 3n, and then -5 for these states right here. Okay. The rest of those would be vibrational states, where it vibrates. Like 1 or 2 atoms move and change that structure. A few atoms move, change structure. If the molecule is nonlinear, you know what these are, right? These are if all the atoms move in the molecule. So if all the atoms move in one direction, that's a translation.
Yeah.
If all the molecules move in such a way that would be an inversion or rotation, that would be those rotations. Yeah, I just want to make sure that you're. So if it's nonlinear, formaldehyde being nonlinear, it's going to be 3n -6, because there's going to be 3 different rotations now. All right, so if we do that for formaldehyde, that's 3 times 4, that equals 12. And so we'll have 3 translations, 3 rotations, 6 vibrations. Those are the 6 vibrations right there. Yeah. Okay, so let's look at those energy states now, like kind of put in, okay? So in general, when a molecule absorbs light, having sufficient energy to cause an electronic transition of vibrational and rotational transitions, that is, it'll change in the vibrational and rotational states, those typically are going to occur as well. Okay? This is why a lot of molecules absorb kind of in ranges, like they absorb bands that have a little bit thickness, right? So if you ever seen a line spectrum, you'll see they have a little bit of thickness to that yellow line, right? They have a little thickness to the orange line, okay? And part of that is because you're seeing the orbital transitions, right? And then around the orbital transitions, you're seeing various different rotational and vibrational, okay? It actually breaks up kind of like orbital transition, big changes, right? In comparison. And then rotational, smaller changes than that. And then you'd have little changes around those, which would be the rotational. Okay? So you have your orbitals changing, then you have vibrational, then you have rotational. Is that making sense? Which is the order of energy for that spectrum of electromagnetic radiation, right? That's why those spark those. Okay? So for example, if you look at a vibrational spectra, you will see thickness to the bands, which is associated, if you get a high enough resolution machine, you'll see individual lines that are actually the rotational. And you can measure those and get the rotational spectra of that. Okay? Okay, I'm trying to make you have connections. All right, so let's go ahead and look at a spectra. These are some of the different conversions we can get. I'm going to use this spectra for a few slides here. So we're going to go through this. So for example, we have a promotion from S0 to vibrational and rotational excited levels of S1. So we have S0 here, S1 here. Okay. And notice that we have these very small energy levels. They always start with larger disconnects going up to smaller ones. Yeah. Okay.
That's 0, that,
Right here.
no, I mean, that's not the base then.
No. This is this set of energy levels that corresponds to the S0 set. Okay. That actually comes from up here, where we're looking at these things before. Okay. So the big thing though is these are your rotationals right here. And these are going to be like your vibrational sets. Okay. So we're doing a vibration. It's going from S0 to S1. Okay. And this is also going to have a rotational energy that's excited with rotational energy, right? And so we could go from the S0 to the S1 here, but we'd also have a rotational energy level that we would go into. Okay. Now, the whenever you do this excitation, you're going to excite it, and this process is going to happen with an absorption, right? Where it's absorbing the photon. That will boost it to the higher excited state. And usually, the first process that happens after that absorption is going to be what's called a non-radiative. Non-radiative because it doesn't radiate energy out, so it doesn't give off a photon. R1, vibrational relaxation. And usually the first thing that happens is these molecules, okay? They're rotating in space, right? Okay. And they're going to have, depending on the energy levels, a distribution of rotations in this set of energy levels, okay? Is that making sense so far? Okay, so you're going to pull one of these from this population. It could be up here, it could be down here, it could be anywhere, okay? So you're going to excite that with your new photon. That causes a vibration. That's going to put it here. That'll be in a corresponding rotational level. Okay. See these wavy lines right here? These wavy lines are corresponding to non-radiative relaxations. Right? So this is going to relax from wherever it got boosted to in the first place down into a lower energy level on the S1. Okay. And that's typically what happens first whenever you do these excitations.
The green bars are
The lowest energy. This is the inter-system conversion right here, is where the green bars happen. So this is where it can go back and forth. This would be your lowest energy level as well. Okay. So this would be the lowest energy level for the S1 vibrational level. This would be the lowest energy level for the T1 vibrational level. Okay. We okay for there so far? Okay. Oh, I'm past time, aren't I? Yeah, shoot. Okay. I guess I'll wrap up right here. Okay, I'll have to try to wrap up about halfway through the next class, so we still have some time to work on the next thing. Okay.
the next class is this.
Hmm?